Okay, we are now recording. Let's get the slideshow set up. All right, where we left off last time, we were just getting to the point of talking about parametric equations. So we've done a little general talk about it. But let's imagine a particle moving along some curve, and I think I described this before. And actually, let me show the curve first, then we'll come back and see. Ooh. Yeah, these are not in great order here. Okay. This could easily be a situation. Here is a particle moving along a curved path here. We're calling the curve C. Okay, for lack of a better term to call it. And initially it starts here, after some time later it's here, sometime later it's up here, and sometime later it just keeps on moving. Okay? Now, if you were to look at that and say, is y a function of x? No. Vertical line test fails miserably in several places. So why are we talking about it? Well, you can take that same curve where y is not a function of x, but introduce a parameter, t, and have x as a function of t, and y as a function of t, and now the various coordinates that they plot out, that gives you your curve. And that indeed is how a lot of things operate. And that's what chapter 7 is talking about, parametric equations, where f of t is some function of your independent variable here is t, not x, not y. Your x is your f of t, your y is your g of t, okay? They're both functions of t. Just for example, the x function starts at this value. As t increases, this increases until it gets here, but then when t reaches this point, then x starts decreasing again. Well, if you plotted x as a function of t, it would be doing something like that. Perfectly good function, right? Perfectly fine function. And x is, y, starting here, y is increasing, then it decreases, then it increases again, then it decreases again. Well, that could be if you plotted y as a function of t, increase for a little ways, decrease for a ways, increase for a ways again, decrease for a ways. As t is increasing, t is changing, increasing always, so your y is changing. You don't have any overlaps in either in x or y. This would look like you did, but you really don't. So yeah, f of t is a function and g of t is a function. So let's back up then. Back up then to the first slide. Yeah, and that was this one. Pretty impressive slide here. X is equal to some f of t and y is equal to some g of t. What we just saw illustrated, thought the illustration was better first and then to explain it this way. And then, now this is, they really, if you then let this be a continuous situation here, then c of t is actually a function of your f of t and your g of t. It's the curve that's drawn, mapped out over time by that f of g of t. As long as f of t is continuous and g of t is continuous, then these things will pair up, and go. You're not going to any jumps here or here, so you will have a continuous function. Now, this is where I get, and I think the whole thing gets a little strange, and I probably shouldn't be saying this yet, but it seems like to me you're almost describing a vector function here. We haven't even talked about vector functions yet, but later we'll see. This is where, just think of it now, that's a curve that was described in the earlier thing that is a function. It's a function of t, not of x and y. Okay. So this is called a parametric equation. Your parameter is the independent variable t, and your intermediate variables are your x and your y, which are represented by f of t and g of t. That gives you a description of that curve, C of t. C is called the parametric curve, and we refer to C of t as the parameterization, which is a really strange word, with parameter t. Now, every time, and you don't see it, but if you got your books there, it seems like to me it should be a parameterization, and I'll most of the time pronounce it that way, but it's parameterization with the parameter t. Because x and y are both functions of t, we often write this expression instead of, slightly different expression. Of course it's going to shrink when I do this. Let me get my pen activated. They'll often write it C of t is equal to x of t, y of t. Okay. Now, this is actually formally a little more correct. These are functions here. You think of x and y as coordinates, and they are, but so rather than say x is equal to f of t and y is equal to g of t, they usually quite often do a shorthand, just x of t and y of t. X depends on t, y depends on t. Okay. So let's do example 1. I think we have it here. Yeah. Sketch the curve. I'm going to do these. Why they have a huge slide here and that little bitty type in the middle. Whoever designed this, or I don't think they had a designer, I think it just happened. That's even small, but at least it's a little more readable. So sketch the curve with these parametric equations. That's called the parametric equations. They're not putting alpha t, alpha g, alpha t and g of t. Just saying, this is your x's follow that pattern, your y follows that pattern. Okay? So sketch the curve with those equations. Okay? Now, what is your favorite way to do curve sketching? Do you like to do t-tables? Do you like to just draw the plot and figure the points and put them in? Or what's your preferred method? Say again? Okay. If you had to do it, what would be your approach? Huh? Just plot straight from here. I don't mind doing that at all. Okay. So let's do y-axis, x-axis. Okay? Now, give me a t. 0. Okay? So when t is equal to 0, what's your x? -4. What's your y? You said 3? So -4, 3, there's t equals 0. Okay? Give me another x. Another t, sorry. Second? 2. Okay, when t is 2, what's your x? Zero. What's your y? Say again? I'm sorry. 7? I didn't plan ahead too well, did I? Okay. I think what I'll do, y'all remember that point. -4, 3, and 0, 7. I'm going to erase that and try again. Okay? All right. Afraid that won't work well either, but at least let's get started. -4, 3. What's the next one? 0, 7. Okay, next. Second. Do 1? T equal 1? Okay, yeah. T equal 1, what would that be? Negative 2, 4. Okay, that'd be right about there. Give me another t. What? Negative 1. Oh, negative 2. Okay, we'll do negative 2. What would x be? Negative what? Negative 8. That's 1, 2, 3, 4, 5, 6, 7, 8. There it is. And what's your y? Second? 7 again. Up here. Okay. Got it? Give me another t. Negative 1. Okay, what would your x be? Negative 6. 1, 2, 3, 4, 5, 6. Okay. And what would your y be? 4. Okay, right there. Okay, I think I see sort of a pattern coming in here. It does look like this is sort of forming a parabola. You can check a few more points. I think you'll see that pretty close to what you get. A lot better looking parabola than what I drew here. That's what you do. So, I don't know if y'all were using the book as your guide for your points that you were picking, but not a bad choice. Okay? And, of course, I didn't do it small enough to get up to 19. I mean, the graph big enough to get up to 19. But that's what you got. And let's see. Let's go and identify those points again. T equals 0 was here. T equal 1 was did we do that? Yeah, negative 2, 4. Yeah, we did that one. So this is t equal 1. I think this was t equal 2, wasn't it? This is t equal minus 1 and t equal minus 2. So you see, not only do you get a parabola, but you get a parabola with a direction. As time is increasing, you're going from left to right on that parabola. Okay? One of the reasons for that is your x is a linear function, but the y is a quadratic function. And it won't get any less than when t is equal to 0. That's as low as it'll go. After that, everything will be higher, right or left. It'll be higher. So sure enough, you get a linear progression on your x-axis and the quadratic expression on your y, dipping down, going back up. So yeah, there's a parabola. Not just any old parabola, a parabola with a direction to it. Okay? Increasing values. And the soul is here. So we're just missing faith. Hopefully you'll be coming in. We just did example 1 at the bottom of page 579, or somewhere thereabouts. I know you have a different book. Now, there's a conceptual insight here. The graph of y is equal to x squared can be parameterized in a simple way. So here we're going kind of backwards on something. There they gave us the parameterization. They said you come up with the graph. Now they're saying, what if we have y is equal to x squared? I'll write it here. Y is equal to x squared. Now that's not that graph, but let's say you do have that as a graph. Okay? Now, how could you come up with a parameterization of that? Here's my little clue. Pick basically the independent variable, which is, second, pretty much x. Choose an x, you'll give me a y, right? So let that be your parameter, right? So let t equal x. Then, so there's your x. X is equal to t, and what's your y equal to? Plug it in, plug it in. Y is equal to t squared. There's a simple parameterization of that y is equal to x squared. Any t you choose, you'll plot the parabola, and that would be the simple parabola, the parent function parabola like we're used to seeing. Okay? Is that the only parameterization that would give you that? You could have said that x equal t squared, then y would be t to the fourth. Would that work well? Not quite as well. Then you only get the positive half of the parabola. Because guess what? You can't get a y to be negative. How about y isn't negative, the x to be negative. So you might do, rather than that one, you would do x equal t cubed and y is equal to t to the sixth. That would allow pluses and minuses. So there's an infinite number of ways you can do that. Okay? So is that what they were getting at now? No, I went a little beyond what they were doing. So therefore, if you have a function that's already a function, y is equal to f of x, just let x be the parameter, the independent variable, and let y be the same function. Y of t would be the same function, your x. So you can make any regular function into a parametric equation just as well. Okay? Y is equal to e to the x. Again, how would you do that? Write that as a parametric equation. X is equal to t. Y is equal to e to the t. Pretty straight. Just choose your independent. If you have the function, y is a function of x, then just use x to be the parameter, and your y is the same. You say, then what's the point? Can't really think of it, but you could do it. All right. Now, as we have just noted, a parametric curve need not be the graph of a function. If it is, however, it may be possible to find that function by eliminating the parameter. Okay? So obviously this is a function. Y is a function of x. No sweat. You can see it. Our good old favorite parabola. Okay? Or a good parabola. This one could not be written y as a function of x. Don't even try to eliminate parameter. You can't do it. Okay? It wouldn't work. Okay? You couldn't get y as a function of x. But if you could, let's do example 2. Okay? Oh my, I forgot. They did do, there was my picture, there was their picture. I wish I had gone to that. Well, I don't know. I like doing it. So this is exactly like we got when we didn't have along the y-axis, and they have that being 4 here, but that being 7, that being 7 there. So their scale is not the same as what we did. Okay, but anyway, that's what you got. We did -2, -1, 0, 1, and 2. So we got this portion down here. If we had along the y scale. Okay. Now, I'm trying to see where in the world this is. This is not in the conceptual thing. This is just, what's that? It's on the previous page? Okay. Where do they? Oh, figure 3. Here they mention it. Oh, I'm sorry. An advantage of parametric equations is that they can enable us to describe a curve that is not a graph of functions. That's what we were talking about before. If it is a graph, just choose your t to be the independent variable, and then the y function or second function will be a function of that. For example, the curve in figure 3 is not in the form of y is equal to f of x. It cannot be, period. But, believe it or not, that is a parametric function. They actually give it to you here. But, boy, don't ask me to tell how they knew that. You know, they knew it because they figured the function first and then wrapped it and then said, well, this has this. But certainly it's the case. Now, you might think that doesn't look like it's really, it looks like it could be three functions, so you just plotted them all on the same thing. It really isn't. Let's just pick a place to start. I'm going to start at this point right here. Let's trace this along. There it goes, up here, down here, over here, back here, here, going here, up here, down here, over here, down, up again, up, down, and finally you get back here. So this has, you actually make basically 3 times around the origin here before you finally connect the dots, okay? So yeah, that is a parametric curve. It is periodic, because after a while you keep repeating that same curve over and over and over. But this is the parametric curve, 5 cosine 3x cosine 2/3 sine of pi 5t. That's your x value. Your y value is 4 sine of 3t cosine 2/3 sine of 5t. Okay. All right. Okay. Just a pretty picture, but you can't do that without a parametric equation. No way you can write that as y as a function of x, because it's not. Vertical line test fails repeatedly on that. Okay, but it is a parametric function or equation. Okay, so now I think this is the one we will see if we can eliminate. So this time what they're doing is initially giving us a curve, a parametric curve. C of t is equal to 2t minus 4, comma, that's the x value, 3 plus t squared. That's the same one we just did, isn't it? Yeah, that's the same one we just did. Sorry. Oh, we did it. Okay, so let's go back to that. Okay. This is it. Let me write it here. In fact, it's already written there. C of t is equal to, open parentheses, 2t minus 4, comma, 3 plus t squared. Okay. A little messy, but doable. That's a big comma in there. Okay. Now, you can see, you can look at that and say, yeah, I know that's y is a function of x, but what y function of what x? Okay? Well, here's what they say. You can solve that, eliminate the parabola. Okay? So, now, since you know that x is equal to 2t minus 4. Now that's the one I would go for because that's a linear equation, both x and t, right? Use this to solve for t. What would that give you? What would you do? Add 4 to both sides of the equation. That gives you x plus 4 equal to 2t. These add to 0. And to solve for t, second, divide by 2. Okay? So now we have t is equal to And there's several ways you could write it. I'm going to write it this way. 1/2 x plus 2. That's not the only way you could write it, but it's one way you could write it, right? Now, let's take this and plug it in your y equation, because you know that y is equal to 3 plus t squared. So that would be y is equal to 3 plus, and it would be 1/2 x plus 2, right, squared. Well, we got a little work to do here. That would be equal to 3 plus sorry, man. Okay, squaring a binomial, remember how to do that? How? 1/4 x squared plus 2x. Excellent. Excellent. Never mind. Okay. Last part's easy. Plus 4. Okay. Now, really didn't need that in parentheses like that. Your y is equal to 1/4 x squared plus 2x plus 7. Okay? Now, a real easy point to check is what? You know it's on that graph. Your y-intercept. How do you get it? Set x equal to 0. First two terms are 0, y is equal to 7. Sure enough, 0, 7 is on that curve. It's up here. Since we have the points here, or we did on our graph, and we can go back and look at those, we can do, say, x equal 1, and that would give you, of course, looking at that, x equal 1 is not going to be perfectly even point, but we can still do it. That would be 1/4 plus 9, so it would be 9 1/4. Okay? So x equal 1, somewhere here, and that would be 9 1/4. That looks like it makes sense. X equal -1 would then give you 1/4 minus 2 plus 7. That would be 5 minus 1/4. Okay? So that would be, what, 4 3/4. And I could easily believe that this would be 4 3/4 there, or pretty close to that. So, yeah, you can go through the whole thing. Let's just go on and do x equal. We did x equal plus 2, didn't we? X equal plus 2, that would be 2 squared is 4. I like that one. 1/4 of 4 is 1. Plus, said 2, that would be 4. That would be 5 plus 7 would be 12. Did I do that right? So what we got, let me go back here and see. No. Oh. We didn't do x equal 2, we did sort of messed up on that one. Sorry about that. We did t equal 2. I'm sorry, I was thinking x equal 2. Okay. Let's do x equal, I still like 2 because it came out well, but we didn't go that far on ours. I don't think we did. No, we didn't get x equal 2. We could have, but we didn't have enough room to do that. But t equal negative, let's go back. What is that point there? T equal 1, we had the point 2, 4. Okay, so let's try that one. Plugging in t equal 2, or negative 2, t equal negative 2, not t equal negative 2, x equal negative 2. X equal negative 2, negative 2 squared would be 4, 1/4 of 4 would be 1. X equal negative 2 times 2 would be negative 4, plus 1 would be negative 3, plus 7 would be 4. And sure enough, our point there was negative 2, 4. Right, so yeah, that's exactly what we got. So yeah, you could plug in any of our points, but you're plugging in not the t's, but the x's. And once you had those points, you could plug them and see they do come out exactly. So yes, that is the normal equation. The parametric equation, frankly, it's a lot simpler. That's a quadratic, but you got fractions, you got 3 terms. Here's just a 2-term quadratic, and it's a linear expression. They're a lot easier to do with, especially on top of your head. Okay, these others give you a headache on top of your head. Okay. Now, for some reason, they wrote theirs in ascending order of the powers rather than descending. And so, all right. Any questions on 2? Okay, I need to go to example 3. Okay, I think that's this one. A model rocket. I hate to say this, but I may have to go get something to drink. I didn't have time for lunch, so I crammed it down real fast and didn't drink much, and I'm beginning to feel that I haven't gotten enough to drink. But let me see if we can go on. Okay, example 3. A model rocket follows this, and I think I'll delete what's here because that was from the last example. I thought this was a slide for it, but it wasn't. So here's what we have. Model rocket follows this trajectory. C of t is equal to 80t, comma, 200t minus 4.9t squared. 200t minus 4.9t squared. Okay. Now, for those who have had physics or are currently taking physics, both of you've had physics 1, haven't you? Have you? Okay. All right. This should sure ring a bell, right? Negative 4.9. So again, 1/2 a, which is g, acceleration due to gravity in the metric system, 9.8, negative 9.8, negative 4.9, 1/2 a t squared. All right, yeah, that's a position, okay? Y coordinate position. Okay, so if that's your acceleration due to gravity in the metric system, I would hazard a guess your initial component of your velocity in the y direction would be 200, because usually your equation is 1/2 at negative 1/2 gt squared, which is a negative number, so that's where I got that, plus v naught t plus x naught, or whatever that is. Well, since you don't have anything here, I'm assuming it's starting from 0, and sure, on the y-axis. And sure enough, it is. Now, what this is telling me, that my horizontal component of your initial velocity was 80. So an initial component of your horizontal was 80 feet per second. So this is the displacement, or the tracing the curve there, and then 200t, this would be the vertical component of your initial velocity, 200. So that was shot at a pretty steep angle up. And sure enough, that looks like it shot at a pretty steep angle up, because your scale is pretty close. So I don't know what that angle is. You can fiddle around with the trig of it. y component for initial velocity, x component for initial velocity. You can, from the tangent, you can figure out what that is. The tangent of theta is equal to 20 over 8, which is 10 over 4, which is 2.5. Okay? Do an inverse tangent of that, you got your initial angle. That's not what we're doing, but for those who have had this before, you can see that. Hopefully. All right. So there's your situation. Model rocket follows that trajectory until it hits the ground. Then it doesn't follow that trajectory anymore, okay? Now, if that indeed is time, do you ever have, when you're launching that rocket, any negative times back there? No, so you're starting here, and you're stopping there. You don't continue here or come from there. That's it, a implicitly restricted domain. Because you've got a rocket, you're firing at t equals 0, it hits the ground sometime later. TF, we'll call it, whatever that is. Okay. Now, the height of the rocket at any time t is your y. That's how far up and down you're going. Okay, your horizontal displacement, or the range of the rocket, is your x. Okay? So, find the rocket's height at t equal 5 seconds. So, how would you do this? R-O-C-K-E-T-M-O-U-S-E. Okay. Rocket's height at t equal 5 seconds. How would you get that? Rocket's height is your y value, and y is equal to this thing. So that would be 200 times 5 minus 4.9 times 5 squared. Okay? Agreed? Okay. That would be how much? 1,000, right? Minus 25 times 4.9. Yeah, you might need a calculator for that one. That'd be 120 something, right? $25 times 5 would be 125. 25 times 4.9, a little bit less than that. So, got a calculator? Hit me. One to 2.5? Okay. 122.5. And that difference there would then be 877.5. So that would be its vertical height at that time. Yeah, 877.5 meters. And this is in meters. I'm not sure if they told you that, but I told you that when I said that's the acceleration due to gravity in meters per second squared, then you know that has to be in meters. Did they ever say it? Yeah, distance in meters. Okay? Now, they also ask you what is the rocket's maximum height. That's the B part. What would be the maximum height? Okay, what would be 0? Okay, the 200t minus 49t squared, would that be 0 there? What would be 0? A little louder. The derivative of that, why is that? Yeah, where the slope equals 0, so that would be the maximum height. You could also think of that as where the velocity equals 0. The vertical velocity is going up, 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 and then when it stops, and then after that comes back down that point where it reaches 0. So the velocity is the first derivative of that. And what is the first derivative of that? So y prime would then be, for this is y, 200 minus 9.8 t. Very good. Oops, I don't need a parentheses there. Okay. Man. Take the break between classes and go drink as much as I can. Man, I'm feeling weird. Okay, and what we do, we set that equal to 0. Okay, faith here, 100% attendance. Way to go, team. All right. Good to see you. All right. We're doing example 3 on page 580, if you have the current edition. 580, right? Yeah. It's chapter 11, 11.1. Okay, how do we solve that equation? Second? Solve for t. So, just because I'm lazy, I put 9.8t is equal to 200, right? Add the 9.8t to both sides, flip sides, whatever you want to do. Okay? Next. Divide by your 9.8. Okay. I don't have a calculator, but that's almost 200 divided by 10. And 200 divided by 10 would be 20. It'll be something a little greater than 20 because your denominator is smaller. The what? I still couldn't hear what you said. Okay, yeah, but I added that to the other side to make it positive and then flip side. I was just being really lazy. Okay. It's 20, I'm guessing 20.2? 20.4, yeah. Okay. So t is equal to 20.4. What's t measured in? Seconds. But guess what it says? It didn't ask for the time of maximum height. It asked for what was the maximum height. So how are we going to have to do here? Plug that back into y of t, only make it y of 20.4 seconds is equal to 200 times 20.4 seconds. I'm glad you got your calculators out. Minus 4.9 times 20.4 squared, seconds squared. Okay? You got your calculators. You plug that along. I really don't feel all that much like doing it. It's not that bad. Let me see. That would be 4,080, 4080, okay, minus, I just don't feel like doing the square in my head. That's a bit much up the wedge. So if you got a calculator, plug that in and see what you get. What you got? 2040.86. Okay, a little bit slower. 2040. Okay. 0.8.6. No, 0.816. Okay. Now, time out here. Being the physicist that I hope all of you are, good physicists, your maximum number of significant digits there looks like it's got to be 2. I mean, the zeros don't usually count, but let's count one of them in each. That would be 2. But I would allow you to go at least to the nearest, to the decimal. 2040 or 2041. Seems like that would be close enough. 2,041 meters. Okay. Now, the book may take it a lot further, and by the way, y is in meters, remember? Let's see, what did they? They rounded to 241 too. Good for them. Quite often math books don't get that part right. We really couldn't go 4 digits like we did, but we'll let them get away with it. All right. Now let's look at some other parameterizations. Before we do it, there is a caution over here. The graph of height versus time for an object tossed in the air is a parabola by Galileo's formula, but keep in mind that figure 4 is not a graph of height versus time. It shows the initial actual path of the rocket. Sorry. Which is both a vertical and a horizontal displacement. Sorry. I'm losing the voice here. Okay. So let's move on to the first theorem, which sort of jumps a brand new rabbit here. And this is the parameterization of the line, which is a very nice rabbit to have. So let's see what that gives us. Let's see if we can blow that up a little bit. All right. A line through a point AB. AB is just any point. X equal A, Y is equal B. Somewhere out there. A slope M is parameterized this way. X is equal to A plus RT, and Y is equal to B plus ST. There's R's and S's, strictly parameters we don't have a clue on yet. In this case, the T, the time, is, oh boy, how do you call that? Well, let's back off just a bit. At time, okay, here's what we're doing. We're starting at that point. Because at time t equals 0, your x-coordinate is A, your y-coordinate is B. Okay? So this is supposed to be good for any times at t. Negative, positive. And so therefore it may not be time, but any parameter t. Okay? And obviously this point AB is when t is equal to 0. Now this is true for any r and any s. Now, number one, we don't let r be 0. But we do say that the slope that they're giving us is the ratio of s to r. Okay? Because this is the y component, x component, so the slope is that ratio of s to r. I don't know if that makes perfect sense to you, but that's what you've got. Any values r and s as long as the slope is equal to s over r. So give me a slope. Make up the slope. Give me a slope. 1 over 2, 1/2. Okay? So your s could be 1 and your r could be 2. S could be 7 and r could be 14. S could be -3 and r could be -6. So any value r and s can do as long as they meet that requirement that the s over r be 1/2. Because you just say positive 1/2, right? Yeah. Now, that's how you parameterize a line through some point AB with slope M. If you know that slope, then you introduce two parameters, one for x and one for y, such that the ratio of the y to x, the slope of the y to x is your slope, M. Okay? Delta y over delta x, that's your slope. All right, the line through P, AB, and QCD. Okay, you're not given a slope. Notice you need two things: point slope or point point. Okay, this time you're given point point with no slope. All right, how do we do that? Wow, out of the sky they give you this. Okay, man, where did that come from? Hopefully, I just gave it away when I said what I did earlier, but it may not have come across that way. What is the slope of this one? Of course, I don't have to shrink it. You can tell me that, can't you? My pen's not working. There we go. Okay. What's the slope between those 2 points? You know it. D minus B over, how about C minus A? You could have done it the other way. It didn't matter which one you started with. I just started with the second one. Okay? Hopefully I got it right. I mean, for what we need here. Okay? Now, they say your slope is any ratio S over R. So, let's make this be our S and this be our R. Why not? Okay? Then let's go up to this formula. X is equal to A, there's your first point, plus R is C minus A times, where did you go? Okay, C minus A times T, and the Y is equal to B plus D minus B times T. And guess what? That's exactly what these give us here. Okay? It's just that they put the T in front and the C minus A afterwards, and the T in front and D minus B afterwards. It's the same thing. We just let that be the S and T. So, guess what? If you didn't know it, I'm not going to sit down and memorize this formula. I might try to remember that one, and then plug this into that, and it'll be fine. Okay? Because if I try to memorize and get all those signs right and stuff like that, ain't going to happen most of the time. Okay? It's going to be messy. Okay? And that's for any value between I have a real big problem with that. They have written, Okay. Anyone notice this? The slide was from the previous edition. That hardly makes any sense at all, does it? Okay. That's supposed to be 0 is less than or equal to T, T is less than or equal to 1. In your book is fine. Your book is probably wrong, right? Yeah. Okay.
It's supposed to be
the T in the middle and the 1 to the outside. When I looked at that, I went, what? Okay. This should be the T, and this should be the 1. Okay. Now, why is that true? Okay. The segment between P and Q is T equals 0 to 1. See, automatically what we've done, just like we did up here, let this be T equals 0. Because when T is 0, that's A, B. Yeah, so this is T equals 0. And when we let T equal 1, this will be A minus A, 0, that will be C, there you are there. This will be T equal 1 here. You'll have B minus B, 0, and you just have D. Yeah, that would be your Y value. So yeah, P is when T is equal to 0, Q is when T is equal to 1. So the segment between P and Q corresponds to the time 0 to 1. So, duh. That at the bottom makes no sense. Okay, now they do have a little proof there, and I think we've basically done part of what that proof is when I showed you how to get this. But anyway, let's move on and do example 4. I don't see, let's see. This is the figure that talks about the proof, I think. Yeah. So we can have that up there when we're talking about parameter ratio of the line. Find the parametric equations for the line through the point P equal 3, negative 1. Obviously, this is not that point, okay? When you're 3 on the X, you'd be negative 1 on Y. No way that could be it. So ignore the figure here. Okay? I've lost my thing here. Of slope M equal 4. M equal 4. Okay? Now, it said find parametric equations for the line. Notice it didn't say the parametric equations, just a pair of parametric equations for the line. Okay, now what's one of the first things you're going to have to do, looking at the A part of Theorem 1, what does that slope tell you? Maybe I'll phrase it a little differently. What if I chose, and to me this is the simplest ratio to have that equal 4 over 1, right? And in our parameterization, we basically let this be the R and this be the S. Is that how it was written there? No, S and R. I always get those backwards because I like to do them the other way, but the book does them this way. S and R. Okay. S and R. Okay. Now, you could use any two that gives you that ratio. I don't care. That's the simplest two I can come up with no negatives or anything else. Live with it. Okay. What does it tell you the parameterization would be then? X is equal to 3. Say again. Plus T. Y is equal to plus 4S. Is that what you said? Is that what? Okay, I couldn't hear what you said. No, yeah, wait. 4T. I'm sorry, 4T. You're right. The S is 4, so you already had the S in there. T. Okay. Now, obviously, when T is equal to 0, that works. Okay. And the Y is going up much faster than the X is, obviously, at a 4-to-1 ratio. That's why the S over R, the coefficients there, S over R, they have to be the ratio 4-to-1. So, yep, we got it. So that's it. I mean, can't think of, that's one parameterization. Okay? Now, we could also write that, remembering it's an equation of a line, C of T, and a curve can be a line. It just doesn't have any curves in it. And that would be this expression, 3 plus T, comma. I like to do 4T minus 1, but I'm sure they don't do it that way. Okay? They probably do minus 1 plus 4T. Okay? Absolutely. Now, is that the only one? No. You can pick any thing. Now, basically, the 3 and the minus 1, they're going to have to stay the same. But you can pick any other ratio that makes S over R be 4. So give me something else other than 1 and 4. Give me one. A ratio that makes 4. Other than 4 and 1. 8 and 2. So this would be plus 2T, and that would be 8T. That will work, right? Or C of T equal to 3 minus 1. I don't have to put the minus 1 there, but I just like to. But I'm going to ask you for a ratio with one of the numbers being negative. Give me one. S equal, R equal. Negative 1 for which? The R? I prefer that, but you don't have to do it. So that could be minus T, and this would be minus 4T. Yeah. That works. So anything, as long as the ratio of S to R minus 4 to 1 is 4. 8 to 2 is 4. 4 to 1 is 4. 24 to 6 is 4. I mean, so anything there would be. Okay? So there's not a unique parameterization. There's actually an infinite number. All right. Make sense? Now, let's go to circles. Circle of radius r centered at the origin has pretty simple parameterization. There it is. Okay? It's a two-dimensional figure, right? So you need two parameters in it. R and theta. Okay? R is the radius. Sorry. And theta is the angle. Okay. Okay. So with that, then this simply works. The x value is r cosine theta, the y value is r sine theta. Okay? We know that from our tree. Okay? And that works. If you've got a fixed radius, then theta could be your only variable, but if you have variable radius too, that's okay to do. Now, what happens if you move that off the origin? Okay? Well, things change now. Okay? Let's see what the problem is, I think. Did I give you a problem here? Okay. Well, they do say this first, too. Stick back with this one. You go around the circle once, as theta goes from 0 to 2 pi. Or from minus pi halves to minus pi halves, minus 3 halves. Minus pi halves to minus 5 halves pi. I mean, you could, anything that gives you a complete revolution there, that would work. You don't have to start at 0. Okay, you can start at some negative number or even the positive number, pi to 3 pi. You have to start here and go right from there. So yeah, anything that will give you one complete loop around. Okay. Now, yeah, they gave this minus pi all the way around the pi. That would work. So anything that gives you a complete 2 pi circularization. Wherever you start, then you're going to end right back on top of it. But it'll have a different value. Okay. So, what if you have a circle not around the origin? How do we deal with that? Okay. Here is a picture of it. Let's zoom in out so you can see it a bit more clearly. Okay. Well, guess what? If it's still got a radius of r, then all you have to do is offset that, a horizontal offset of A, a vertical offset of B, be A plus r cosine theta, comma B plus r sine theta. Okay? And that gets you with the center up here at AB, and then you go one revolution around it. That's all there is to it. So it's pretty simple to offset a circle. Now, if you're doing other things to it, it may get a little more complicated, but just the offset is pretty straightforward. Now, for that to be usable, you need to know what your R value is, what is the radius of the circle, and theta then turns out being your only variable. Okay. If you don't know the r, you have to be given one or make up one. And who knows if what you make up is going to be, I can't lost the train of what I was saying. It doesn't really matter. Certainly the angles, as long as you make one completely, you can start those anywhere. Okay. I think they do the same thing here. They show what they just showed there is your, for any circle centered at offset from the origin from 0, 0 to AB, just add an a to the x value, add a b to the y value. Now, keep in mind the a's and b's could be negative too. A negative a would put you over here either in the third or the fourth quadrant. The negative b would drop you down to either in the third or the second or the third quadrant, and the negative b would drop you down to the third or fourth quadrant, depending on what a was. So they can have any sign value, any SIGN sign that you want. Okay. Now they have a little all right. I think probably makes the most sense to go back here. Let's pick any point here. This has a value xy. Okay? That point right there has some value xy. Okay? Now, if indeed this is your x and this is your y, okay? So if you've got some point there, x minus a squared plus y minus b squared that is sort of your generic expression of the equation of a circle. Okay? And what makes it a circle is that your x's and y's have the same coefficients. If that was a 1x and a 3y, that's going to be an ellipse. Okay? If the minus sign was in there, that's going to be a hyperbola. So this is the core definition, or at least the beginning of the left-hand side of a circle. The right-hand side is typically the radius squared. Okay? So this is a circle whose center is offset to A, and whose the x component of the center is offset to A, and the y component is offset to B. And B and A can be positive or negative. A is positive, then you're going to the right. B is positive, you're going up. But if A is negative, you're going to the left. If B is negative, you're going down. So then you'd have pluses here if those were negative, if you actually have the numbers in there. So they're checking to see if indeed this does give you the equation of a circle. Well, if your x is that, then x minus a would be x, well, I'm sorry. Okay. If your x is this, that would be a plus r cosine theta minus a, comma, squared, plus the y is b plus r sine theta minus b, because this is your x, there's your y, and then you're subtracting a or b from it. And that would be squared. Well, your a minus a is 0, b minus b is 0, and this is r squared cosine squared theta plus r squared sine squared theta. And that would be what? Factor out an r squared, and that leaves you cosine squared theta plus sine squared theta. And what is that? Always sine squared theta. 1. That's always 1. So sure enough, that equation is equal to r squared. That is your standard equation for a circle. Okay? Now, not really sure why they did that, but since they did it, we went on and did it too. Now, in general, to translate, that means to move a parametric curve horizontally a units, vertically b units, replace the c of t, which the c of t, which was x of t, y of t, to plug in what they are. A plus, you're moving a units to the right and b units, that up vertically b units. And a could be positive or negative. So it could be horizontally a units, vertically b units. But you started at x of t, y of t, your original x, y values. Now that new curve will be at a plus x of t, comma b plus y of t. That's your translation. Suppose we have a parameterization, c of t is equal to x of t, y of t, where x of t is an even function and y of t is an odd function. Okay. Okay. Then, because your x, since x is an even function, x of minus t is the same as x of t. But y is an odd function, so y of minus t is minus y of t. So in this case, c of minus t is a reflection of c of t across the y-axis. Okay, I don't know if you caught that. Let's do that. I think I'll take this off. Just trying to see how much I could just say. Yeah. What is what? Okay. These things here, x of t is equal to this, y of t is equal to that. Okay, I just deleted. Let me see. I don't think I can go back to it. But okay. I'm trying to remember how far, back we're talking about. If you did x minus a squared plus y minus b squared, is that what you're talking about? Yeah. That's at least the beginning of an equation of a circle. When we plugged these things in, we found out it went to r squared. Indeed, that is what an equation of a circle is. Okay. Yeah. Okay. Now, I was trying to think how much of this we need to do. I'm not sure all the importance of this, but let's do it since they say it. Suppose we have a parameterization where x is an even function. X even. Y odd. Now what x even means is that x of a minus t is the same as x of t. That's the definition of an even function. If you do so far to the left, you get the same thing if you go the same distance to the right. Okay? I should say right, left for you, both of them pointing in the opposite direction. Okay. Y as an odd function means that y of minus t is equal to minus y of t. Okay? Now, what if you had then a function c of t is equal to x of t, comma y of t? Okay, that's your curve that's being formed by those. By those parametric equations. Okay? Now, what we're interested in is what is the even or oddness, if it has any, of c. So how do we investigate that? We see what c of minus t would be. Okay, c of minus t would then be x of, oh, yuck. Okay, x of minus t, y of minus t. Okay, which would be x of minus t is just x of t. There, I did it again. X of t, and y of minus t would be minus y of t, because y is an odd function. Okay? Now, is that the same or the opposite of what c of t is? Okay? Well, the x components are the same, the y components are the opposite. So this looks like a neither to me, but what they're saying here is it's a reflection across the x-axis. Because guess what? This means the x's stay the same. So if you had x of t and you have these two functions, but your y's are opposite of each other. So if your x was like this, your y, the x is going to stay the same, but the y is going to be exactly the opposite. So that means you have a mirror reflection across the x-axis. We haven't had that before in functions. Not really. We had even functions that were reflections across the y-axis, and odd functions which were reflections across symmetric about the origin, but we didn't have one here. This now gives us something that's symmetric across the x-axis. And I guess that's all they're saying here. So, therefore the curve is symmetric with respect to the x-axis. Okay. Now, let's see what example 5 gives us. I think I'll just clear this out of the way. Okay. I mentioned it, and now it shows up. Parameterization of an ellipse. Okay. Now here is the standard equation of an ellipse. X over a squared plus y over b squared is equal to 1. Okay? That's your standard equation for an ellipse. Now, if you're not used to seeing it in that form, what you could do, I'm not suggesting that you do, you could multiply by your least common denominator, in this case would be a squared b squared. And if you multiply both of those by a squared b squared, all three terms of that, this would be bx squared plus ax squared is equal to a squared b squared. Okay? Which would be another way to express an equation of an ellipse. Now this is one centered at the origin. Well, yeah, the ellipse is centered at the origin. If you were displacing that, you'd have a y minus r squared, or x minus r squared, y minus s squared, or something like that, that can show you your displacement from the origin. But we're just doing it with respect to the origin now. Okay. Now the question is, show that an equation with this standard equation for an ellipse is parameterized by this. C of t is equal to A cosine of t, comma, B sine of t. Now, remember what your parameterization for a circle was? R cosine t, R sine t. Both of those have the same coefficient. The trig functions are in the right order, and that gives you everything with a radius r. This now gives you something with one axis of radius, length A and the other of length B. So either you're going A units this way and B units this way or something like that. So it won't be, is that A and B are not the same, then you get an ellipse. Okay. And this is good for minus pi less than or equal to t. That gives you just one time around, okay? You don't want to just keep going over and over and over. Okay. We first need to verify that an ellipse with this equation is parameterized by that. So let's do it. This is your x of t. This is your y of t, right? And let's do what they told us up here. They said this is, you're going to square that, right? That'd be a squared cosine squared t over a squared, okay? Plus, and when you square the y, you get b squared sine squared t over, b squared equal 1, okay? The a squareds go out, the b squareds go out, and what do you have? Cosine squared t plus sine squared t is equal to 1, and that's always true. So you have now verified that indeed that gives you the equation of an ellipse. Now, it says plot this when a is equal to 4, b is equal to 2. So I think what I'm going to have to do is clean the page and then probably write some stuff over again. Okay? So here's what we're trying to plot. C of t is equal to 4 cosine t, comma, 2 sine t. Okay. Okay, something like that. Oh my goodness. How do we do these curves? Remember me as a cheerleader? I'd say, give me a T. Right? So give me a T. Give me a T. 1. Give me another T. 0. Let's start with 0. Okay? All right. So C of 0 would be 4 times, what's the cosine of 0? Second? 1. Okay? 4 times 1 is 1. Comma 2 times the sine of 0. What sine of 0? 0. So there we have it, 4, 0. Okay? Give me another t and don't make it 1. Okay. Pi halves? You like pi halves? I like pi halves. What would that be? What's cosine of pi halves? 0. 4 times 0 is 0. And what's sine of pi halves? 1. So that would be 2. 0, 2. Oh, I'll put those in right places, didn't I? Okay, give me another t. Oh, I like it. Okay, y'all are catching me. Okay, yeah. Okay. What's the cosine of pi? -1 times 4 is -4. Sine of pi times 2 is 0. So -4 is 0. There we have that one. C of 2 pi, say again? 3 pi over 2. Okay. Couldn't hear. That would be what? Zero. I believe it's 2. Negative 2. Well, sine of 3/2 pi is -1 times 2 is be -2. So that would be down here. Now, if you wanted to plot some more points in between, knock yourself out, okay? But this is going to be a nice, well, nicer than that, egg, okay? Football, something, okay? There would be your ellipse, okay? They did a lot more points in between. Fantastic. Go for it. Now, what was the t doing? It was increase. Oh, we didn't do it right, did we? I forgot to write the whole problem here. We were supposed to be doing minus pi less than or equal to t is less than or equal to pi. Isn't that what they told us? I forgot they said that. So I should have started with minus pi. And if we had started with minus pi, we didn't do that. Where is minus pi? Over here. So that would have been my first point here. Okay. And then we would have done minus pi halves, which would have been here. That would have been the second point. Then we would have done 0, which was up there. Then we would have done pi halves, which was there. Pi halves, which was in back here. Yeah. So we started in the wrong place. But wherever you start, you're going in this direction. So that is the direction of that. Whether you start at 0 or start at minus pi halves or start wherever and just go one loop with 2 pi around, you're going to complete one path. Parametric curve, C of t, is also called a path. I think we've been calling it that. Goodness gracious, my throat is so raw. The term emphasizes that C of t describes not just an underlying curve C, but also a particular way of moving. That's what I've been saying. The arrow tells you it's not just a curve, but it's a direction. It's a directed curve. That's what they mean by path. So their conceptual insight here, the parametric equations for an ellipse in example 5 illustrate a key difference between the path C of t and the underlying curve C. The curve C is of an ellipse in a plane, whereas that's a capital C, whereas little c of t describes a particular counterclockwise motion of a particle along the ellipse. If we let t vary from 0 to 4 pi, then the particle goes around the ellipse twice. A key function of the parameterization is that they are not unique. In fact, every curve can be parameterized, I already said this, in infinitely many different ways, and we went over some of those before. All right. Let's do example 10. I think, well, let's get started on example 6. Where did 10 come from? I'm not sure. Okay. I'm not seeing that equation on the page. Oh, no. Did I go backward somewhere? wow. That was back at equation 5. I didn't advance very well there. Ah, there's our ellipse that we were just doing. I'm sorry I didn't get it on the right thing. There is the ellipse. We just chose 4 points. They chose a lot more. And they chose t's of 0 to pi. They should have done minus pi to 0 and then 0 to pi. But this shows those points. We just did this one, this one, this one, and that one. Obviously, those work well. They did pi 6 is equal to pi 6, doesn't that make the x value square root of 3 over 2, and this is half of that, which is 1. This is square root of 3 over 2 times 4, and this is 1 half of 2, which is 1. And then this one would be 1 half of 4, which would be 2. Go. Okay. And this was the table that they used to get those values. I would have done the table first. Okay. And then they back up and do that. My goodness, we've already done that a while back, didn't we? No, this is the that's the equation we were doing for the parameterization, and they already showed the results. This is here we finally hit it. And by the time we got there, we ran out of time. So catching up with where we'll begin with example 6 next time. I think you got enough covered today to do a few homework exercises. On here, you can do any of the odds 1 through 5, any of the odds 7 through 13, do either 15 or 17 or both. I think you can do 19 or 21. I think you could do any of the odds 23 to 37. And I'm not, let's see. I think maybe we can stop there and we'll pick up the rest of those next time. All right, not moving as fast as I hope, but part of that is I'm feeling so lousy. So we're going to do 11.1 and 11.2, and 11.2 is pretty short. We're not going to do polar coordinates. I recommend you try them, take a look at them, especially if you're going to use them in your field of study. But after we finish 11.2, I'll give you a take-home test on those 4 sections, 10.1, 10.2, 11.1, and 11.2. We'll move on to chapter 12 then, where the real part of Cal 3 should be being, but you really need this to get that. When we finish 11.2. Yeah. And it's a take-home, so I'll give it to you. Yeah, I would say either Tuesday, either Monday or Wednesday. Probably Wednesday is what my guess is. Because I just may not have time to get it made out by Monday, but we'll see. All right, good deal. Before I close up shop here, let me end the recording.